What is up, engine heads? Today I have something really exciting for you. A brand new inline 4-cylinder engine. One that has the potential to be a really big deal. It has the potential to be a really big deal because it claims that it has overcome the single greatest limiting factor of any inline 4-cylinder engine, and that is its displacement. Now, to understand why this engine could be such a big deal, we first have to understand why every inline 4-cylinder engine is limited when it comes to its maximum displacement. Now, if you've been watching any of my previous videos where I talk about the engine balance of different engine configurations, you've probably noticed that I talk a lot about primary and secondary engine balance. Now, primary and secondary engine balance or imbalance is one of the single greatest design concerns of any engine configuration. Now, if you already know about these, you can use the timestamps in the video below to skip right to this brand new inline 4-cylinder engine that I want to talk about today, or you can keep watching for a detailed explanation of primary and especially secondary engine balance, which will help you better understand why this engine has the potential to change the game. Now, the piston reciprocates. It moves up and down. The crankshaft rotates. But the connecting rod is the complicated one because it both reciprocates and rotates. It has a very complex motion happening. And to understand why this is a problem, we have to start from the basics. And the basics are this. The distance from the topmost position of the piston, or TDC, or top dead center, to the bottommost position of the piston, or BDC, or bottom dead center, this distance between these 2 points is called the stroke. This is the distance that the piston travels during every single stroke of an engine. For the sake of simplicity, let's imagine that this engine has a stroke of 100 millimeters. So, every piston stroke is equivalent to 180 degrees of the crankshaft's rotation. So when the crankshaft is at 0 degrees of rotation, the piston is at TDC, or top dead center. When the crankshaft rotates to 180 degrees of rotation, the piston is at BDC, or bottom dead center. So logic tells us when the crankshaft is at 90 degrees at the half point, at half of the stroke, the piston should also be at half of the stroke, right? The piston should be at 50 millimeters of, distance covered. Well, if we actually rotate the crankshaft to 90 degrees on any reciprocating piston engine, we're going to find out that the piston has actually covered more than half of the stroke. In our case, if the stroke is 100 millimeters, it's usually going to be somewhere between 55 or maybe 65 millimeters. So why is this happening? It doesn't seem logical. If the crankshaft is at half of the stroke, the piston should also be at half of the stroke. Why does the piston cover more than half of the stroke during the first 90 degrees of the crankshaft's rotation? Well, the culprit behind that is the connecting rod, because it moves in this complicated pattern of motion. And to understand why this happens, we have to look at the connecting rod by itself. We have to isolate the connecting rod. Now watch. When the engine is at 0 degrees of rotation, when the crankshaft is at 0 degrees, we can see that the connecting rod is fully upright, right? It's standing perfectly straight. But once we rotate the crankshaft to 90 degrees of rotation, we can see that the connecting rod is definitely no longer standing upright. It's now at an angle, it's sloped. And if we isolate the connecting rod, we can see that the vertical measurement of the connecting rod standing up straight and at an angle is obviously different. The vertical measurement of the angled connecting rod is shorter than the straight connecting rod. So for example, let's imagine that at an angle, this connecting rod is 8 millimeters shorter. Its vertical measurement is 8 millimeters shorter than the connecting rod when fully upright. What this means, it means that as the connecting rod angles during the first 90 degrees of rotation, it's going to pull down the piston by this additional 8 millimeters. So instead of covering 50 millimeters during the first half of the stroke or the first 90 degrees of the crankshaft's rotation, the piston instead covers 58 millimeters. So why does this even matter? I mean, who cares? Well, physics cares. We know that force is mass times acceleration. Obviously, the piston's mass doesn't change. As the engine is running, the piston doesn't gain or lose any mass. But what the piston is also doing as the engine is running is that it's constantly accelerating and deaccelerating. For example, starting from top dead center, the piston accelerates downwards and then it reaches its maximum velocity somewhere at the half point of the stroke. And then as it's going down towards bottom dead center, it slows down. It has to deaccelerate, and then as it reaches bottom dead center for a very brief moment of time, it stops, changes direction, and then again accelerates away from bottom dead center. So the piston is constantly accelerating and deaccelerating. The problem is that during the first half of the stroke, during the first 90 degrees of the crankshaft's rotation, the piston is covering a greater distance. Because it's covering a greater distance, it has to accelerate more during the first half of the stroke, which means that the forces associated with the piston during the first half of the stroke are unequal to the forces associated with the piston during the bottom half of the stroke. The mass is the same, but the acceleration is different. The faster something is moving, the greater its inertia. The greater the inertia of something, the harder it is to stop. The more force we need to stop it. And this difference in inertial forces between the top and bottom half of the piston stroke are the source of secondary engine imbalances. The inline 4 has good primary balance because it has an even number of pistons. Each piston mass can be balanced out by the mass of another piston. But when it comes to secondary balance, the inline 4 is a pretty terrible configuration. It's bad because when two pistons are accelerating to or away from TDC, the other two pistons are doing the same thing but at BDC. They're always at the opposite ends of the stroke. This means that the difference in inertial forces between the top and bottom or first and second half of the stroke are made very apparent in the inline 4 engine. And then this force inequality is made even more apparent by the fact that the pistons are moving in pairs. So now we're equipped with the knowledge to answer the question why the inline 4-cylinder engine is limited when it comes to its maximum displacement. So obviously the larger the displacement of the engine, the larger you have to make the pistons. The larger the pistons, the greater their mass. And here we have two imaginary inline 4-cylinder engines. As you can see, they have the same difference in acceleration between the top and bottom or the first and second half of the engine stroke. They do have different pistons, however. The first engine has a small mass piston and the second engine has a piston with a greater mass. And as you can see, although the difference in acceleration is the same, the forces associated with the top and bottom half of the stroke are different. They're larger in the engine that has the larger pistons. And the larger the forces associated with the top and bottom half of the stroke, the larger the difference in force, the more destructive the vibrations associated with secondary imbalances. Actually, there's a disclaimer here. You can in fact make a very large inline 4-cylinder engine. However, you have to sacrifice something, and you have to sacrifice RPM, the max RPM potential of the engine. And this answers why any large mass-produced inline 4-cylinder engine ever made has been a low max RPM diesel engine, either in a truck or maybe a stationary power generation diesel engine. Gasoline engines, performance-oriented inline 4 gasoline engines that have been mass-produced have always been limited to a maximum size of 3 liters. You cannot find a mass-produced inline 4 gasoline engine larger than 3 liters. And even at this size, they need band-aids to prevent them from shaking themselves apart. And these band-aids are called balancing shafts. A balancing shaft is just that, well, a shaft. It's a rotating shaft with an offset mass or weight on it, and it rotates together with the engine. And by doing so, it tries to counteract the forces associated with primary or secondary engine imbalances. But there's a problem with balancing shafts. They're simply a necessary evil. Nobody really wants to use them because they don't fix the root cause of the problem. They only fight the symptoms. Balancing shafts add weight, moving parts, and thus complexity and friction to an engine. The balancing shafts needed to fix an inline 4 are especially bad because secondary vibrations occur twice per every engine revolution. You need 2 balancing shafts that rotate at twice the speed of the engine for an inline 4. That's a lot of moving parts and a lot of friction. But if we ignore the secondary balance issues, the inline-4 is a really nice engine configuration. It's a great all-rounder. First of all, it's really small and compact, so you can fit it into a really wide variety of vehicles. It also doesn't have too many moving parts, so it isn't overly complex, heavy, or expensive to manufacture. It's also pretty smooth because it has a really nice primary balance and it doesn't have any gap between power strokes. Also, because it doesn't have too many cylinders and too many moving parts, it doesn't have too much friction, which means that it's pretty efficient. And efficiency is the name of the game today. Efficiency is the reason why so many different types of vehicles have been moving towards engines with fewer cylinders. In theory, actually, the inline-4 could do everything a V6 or V8 do if we could make the inline-4 with sufficiently large displacement. But to make a large inline-4, we need to add balancing shafts. And even with balancing shafts, the inline-4 is limited when it comes to displacement, but let's imagine that it isn't limited. The problem with balancing shafts is that they're self-defeating. We're using the inline-4 because it has less moving parts and less friction than an engine with more cylinders, but then we're adding friction and adding parts by using balancing shafts. It really doesn't make that much sense. If only there was a better way to make the inline-4 have more displacement. Well, apparently there is. Now, a few days ago, I was fact-checking and doing research for one of my future videos, and then I stumbled upon this page. This is the Start Engine investor page for Alfadan Incorporated. Never heard of them? Well, neither have I. Well, apparently they're making a brand new marine outboard engine, and they're looking for investors, and they have already raised more than $1 million. But that's not what's interesting here. What's interesting is that this brand new engine is an inline-4 cylinder that aims to outdo V6 and V8 competitor engines at pretty much everything. Now, I'm not really familiar with the outboard powered boat industry, but apparently the problem with these boats is that they have been growing in size over the years, and the solution to this growth was to simply fit more engines to push the boat through the water. Although this works, it really is very far from an ideal solution because more engines means more drag, more weight, more maintenance costs, more friction, more fuel consumption. You know, you do get to move the boat at the same speed as if the boat were lighter, but you're really paying a big penalty for that. Now, this is where things get crazy. Alfadan claims that their brand new inline 4-cylinder engine is 50% more powerful, with 50% less weight and 50% moving parts than all competitor engines. So what takes 6 competitor engines, now you can do the same with only 3 Alfadan inline 4 engines. Yeah, I've been around long enough to know that something that seems too good to be true is usually just that. It's too good to be true. But nevertheless, this caught my attention, so I get kind of curious and I decided to, keep reading. And then here, as you can see here on the page, they say they're mentioning the inherent secondary balance issues with inline 4-cylinder engines we just talked about at length in this video. But down below, they claim to have solved this issue by completely redesigning the inline 4-cylinder drivetrain, which will make it possible for Alfadan to produce the very first large displacement inline 4-cylinder engine. Okay, bold claims. So I kept scrolling down and things got pretty serious pretty quickly. Apparently this isn't just some sort of empty claim. In fact, a proof of concept of this brand new revolutionary inline 4-cylinder engine and a feasibility study has already been done. And not just by anyone, it has been done by Mahle Powertrain. Now, if you're at all familiar with cars and engines, you know that Mahle is one of the most reputable names in the industry when it comes to engines and engine parts. For example, the pistons in the Bugatti Veyron are made by Mahle. I think that says enough. Mahle has been at the forefront of engine downsizing, turbocharging, and efficiency improvement for more than a decade. But that's not all, because these guys, Alfadan, they have another big name behind them. Freevalve. You definitely heard of these guys. It's the sister company of Koenigsegg Automotive that has been making news headlines for quite some time because they developed a cam-less engine. Cam-less as in no camshafts. Instead, each valve is pneumatically opened and computer controlled, which means infinite possibilities and infinite control over how long and how much the valve is open, which means infinitely increased power potential and possibilities. But also it reduces the size of the cylinder head because there's no camshafts, no cam gears, no timing chains, no timing belts, which means dramatically increased efficiency, dramatically reduced friction. Basically, it's a very big deal. So we have a brand new inline 4 cylinder that not only is going to be using free valve, but also it has a completely redesigned inline 4 drivetrain that has apparently solved the secondary balance issue of the inline 4. It's pretty much the only issue of the inline 4 cylinder engine. So obviously I get pretty excited about this, and I decided to get in touch with Alfadan. Honestly, I didn't expect much in terms of communication, but guess what? I ended up speaking to the CEO of Alfadan, Albert Araujo. And turns out Mr. Albert is an engine head just like me and a lot of you guys here on this channel, so we ended up speaking at length about the inline 4 engine, the challenges, the potential, and so on and so forth. Now, there has been a lot of development already done on this engine, but it isn't going to be released just yet. So Mr. Albert had to protect the intellectual property of Alfadan, the company, so he really couldn't tell me exactly how this works. But what he did tell me is this. He told me, we have reinvented the connecting rod. If there has ever been a big bombastic claim when it comes to inline 4 engines in the last, 50 years, this is it. It's a pretty big deal, and I really hope it means what it means, because if it means what it means, it really is going to change the game, and it's going to make the inline 4 cylinder engine such an incredible powerhouse. Now, in addition to telling me this, Mr. Albert did tell me that the engine they're currently working on, the 654, this is the rendering of the engine based on actual SolidWorks files of the engine, so this is a very accurate rendering. And he told me that this engine is, listen to this, naturally aspirated. It's 7.5 liters, inline 4, capable of running at a continuous RPM of 5,500 RPM, and it makes 654 naturally aspirated horsepower. Inline 4. I dare you can go to any library, you can scour the internet, you can look at every single file and piece of information ever released. I guarantee one thing, you're never gonna find a mass-produced inline 4 at 7.5 liters that does 5,500 RPM. So obviously this is a big deal. It has the potential to completely change the game if this engine becomes a reality, if it hits the market. And to me, it looks like it has good chances of actually becoming a reality, because it doesn't look like just another crowdfunding effort, because it does have some pretty big names behind it, and it has a feasibility study, and it has a proof of concept. So I really hope it becomes reality, because I'm also really curious about that reinvented connecting rod. How exactly does it work? How exactly does it eliminate secondary balance issues? I'm really curious about that. But also, this has the potential to not just completely change the outboard powered boat market, but it can trickle down from that market into, for example, the car market. In the future, we might see, really capable cars that have a relatively compact, large displacement inline 4 in them, making giant power, but also at the same time improving efficiency, reducing friction, cost, and maintenance because it has less moving parts. But also the engine is compact, so it opens up the constraints of vehicle design and improves vehicle dynamics and how and where you can place the engine, because you can obviously place an inline 4 in many different ways, while you really can't place a V8 in many different ways. So as you can probably tell, I'm pretty excited about this, because it is really interesting. So yeah, the only sad piece of information is that this is all the information I have at this point. But Mr. Albert Araujo did end the phone call with me, telling me that they will do their best to include me in any future updates on the Alfadan engine. So when there are any future updates, I hope that I'll be among the first to share them with you guys here on the channel. So yeah, I'm not very good at being patient and waiting for updates, so that's why in the meantime we will keep ourselves busy on the D4A channel with other really fun and interesting topics coming in the future videos. So yeah, that's pretty much it for today. As always, thanks a lot for watching, and I'll be seeing you soon with more fun and useful stuff on the D4A channel.